We can see okay. Don't need lights off. Good. Yeah. Okay. So chapter 1 here, we're not going to necessarily talk about everything in chapter 1. We're going to hit some highlights of it, if you will. We're going to talk about some important ways to punch some things into your calculator here in chapter 1. Talk a little bit about what chemistry is, a little bit about scientific methods. So we may not go through every single slide on this one. So let's get a little bit into chemistry here. So chemistry is obviously a science that really does affect all aspects of our life. There is, as you can see here, forensic scientist, involves a lot of chemistry. Things like food scientists, right? The food we eat involves chemistry. Medicine, even cosmetics, right? So there's chemistry that goes with that. So chemistry really does sort of interplay in a lot of aspects of our lives. And a lot of what we deal with in terms of chemistry is the study of matter and really sort of how it's changed or how it resists change. So a lot of things that we study is composition of matter, structure, properties, how things react. And it again happens all around, right? When we plop, plop, fizz, fizz, as we see there, it's a little bit of Alka-Seltzer. That's actually a chemical reaction happening when you do that. It's also why you take something like an antacid, because it's reacting with the acid that's in your body. And that is also a chemical reaction, a neutralization reaction that is happening. So when we talk about chemistry, we think about, what are things made up of? How are they sort of put together? And different properties that they possess, either physical properties, chemical type properties, and a lot about how they do react. And when we talk about chemistry, a lot of it does deal with matter. And matter is really anything that occupies space and has mass. So pretty much everything along the way here. And when we talk about matter, there's really sort of 3 states of matter that we oftentimes deal with. We have the solid state of matter. And typically speaking, in the solid state of matter, atoms, molecules, they're pretty much packed in there pretty tight to one another. And this is why when we think of things that are solid, they have a pretty rigid shape. They're hard to change the shape of because everybody's pretty much packed in there tight to one another. The next state of matter that we oftentimes will deal with in chemistry, if I get my pen, is the liquid state of matter. And in the liquid state of matter, we still have everybody relatively close to one another, but there is a little bit more room for movement that's happening here. And that's why when we think of liquids, right, we think of them as being fluid. And that's because they have actually enough energy, the molecules and the atoms, to pass one another, which is why it gives that sort of fluid characteristic that we don't see in solid, because in solid, they don't have a lot of energy. They sort of lock themselves into place. Nobody's really moving past one another. And again, that's why we don't really pour solids, or they all come as one. They don't really are fluid like we see with a liquid. The last state of matter is the gas state of matter. And in the gas state, that is really the state of matter where we have everybody completely broken apart from one another. They're flying around. And as we'll talk about when we get to the gas chapter, that's what we associate with gases, which is pressure. As they're flying around, there's collisions that are happening, and that causes the pressure that we associate with gases. So a lot of what we deal with, for example, in chemistry deals with the state of matter. As matter sort of transforms from one state to the next, those are certain types of processes that occur. When we go from solid to liquid, for example, that is the process of, what is that? If I take an ice cube out of the freezer, it will start to melt. Yeah, so that's the process of melting, right? If you take some liquid water, put it back in the freezer, going from liquid to solid, that is the process of freezing, right, that occurs. As we go from liquid to gas, that is the process of evaporation, or sometimes referred to as vaporization. And as we go from gas back to liquid, that is the process of condensation. Like when you take a shower, right? The mirror has a lot of water on it, right? That is condensation basically occurring. We also can have some transitions as we go from solid, skipping the whole liquid cleanup along the way. That is what is known as sublimation. Perhaps you're familiar with dry ice. Dry ice, which by the way is not water, it's actually carbon dioxide, is something that goes from the solid state directly to the gas state. No liquid cleanup, and that is sublimation. We also could go the opposite way. We could go from gas, once again, skipping the whole liquid mess and end up as solid. That is what is known as deposition, like you're depositing something. If you've seen a CD, a DVD, you could Google it, I suppose, nowadays. They're very shiny, and that's how they get very shiny. They actually deposit metals on top of them to give them that sort of shine. So a lot of what we deal with are these sort of transitions of phase, is sometimes referred to, or state. For example, these processes here, melting and freezing, does that occur at the same temperature or different temperatures? It actually occurs at the same temperature. So the process of melting and freezing, and by the way, evaporation and condensation also occurs at the same temperature. This is what is sometimes referred to as the normal freezing point or melting point of a substance. So for example, if you took something like water, that's 0 degrees Celsius is where that occurs. Water is 0 degrees Celsius, the freezing point and melting point. If you are exactly at 0 degrees Celsius, right at 0 degrees Celsius, you actually have both things happening at the same time. You have kind of like ice crystals. So you got a little bit of solid ice, got a little bit of liquid water happening. And it's not until you get a little bit above 0 degrees that you actually sort of transition into liquid water, not until you get a little bit below 0 degrees that you transition fully into solid. Same thing happens at what is referred to the normal boiling point of a substance. And for water, that is 100 degrees Celsius that occurs. At exactly 100 degrees Celsius, you got a little bit of both happening there. You got gas, you got some liquid. It's actually what occurs at the surface of any liquid that you have. You have certain molecules that are in the liquid that actually have enough energy to escape the liquid. And you have certain molecules that have less energy that kind of drop back down and go for a swim back into the liquid component. That is why, right, when you have a little bit of liquid out, it will eventually evaporate, right? Because you have molecules just jumping out of solution, right, into the gas phase. By the way, we'll talk more about that, but air blows them away, so they can't come back in, and eventually it will sort of evaporate off. So a lot of what we deal with are these sort of changes, and also energy is an important part of a lot that we deal with in chemistry. So if I go from solid to liquid to the gas phase, would those be processes that require energy to be put in or removed? Yeah, you would have to put energy in. So if you just think about that ice cube example I mentioned, if we take an ice cube out of the freezer and just put it on the table, although we may not be directly heating it, the ice cube will be picking up the energy from the surrounding air, right? And heat and energy, or heat flows from hot to cold, right? So when you take your ice cube out, it is colder than the air. That means the energy from the air is going to be transferring into your ice cube and will start it to melt. You can make that occur faster by heating it up, right? You can put a flame under it, you put it on a hot plate or something like that, and it will start to heat. Just like when you go to make some pasta for dinner, right? You start with some water in a pot and you heat it, right? And it starts to boil, which is this boiling point. And that is where that liquid water is then going to change into gas phase. And that's the steam that you see coming out as it's starting to boil. That steam is water in its gas state, right? It has now escaped the liquid and it has a lot of energy to do that. So as we go from solid to liquid to gas, these are all processes that energy is absorbed. And one important sort of principle in chemistry is when we have a process where energy is being absorbed by something, That is what is referred to as being endothermic. So endothermic processes are all processes where heat and energy is being absorbed by something. And as we go from solid to liquid to gas, that is essentially what's happening. As you could probably then imagine, if we were going sort of in the opposite direction, heading from gas back to liquid, back to solid, those are all processes where energy actually has to be released in those processes. So energy has to be released. So if you think about it, if you start in the gas phase, you got these molecules flying all around. As they lose energy, would those molecules be flying faster or slower? It would be flying slower. Like if you lost energy, right, you would be like walking slower, like on flight number 9 of the stairs that you're walking up, right? You're not as probably fast as like the first flight of stairs that you did, right? You lose a little bit of energy. And the same thing happens here as those gas molecules lose energy. They come in contact with other gas molecules, which now they no longer have enough energy to escape each other. They kind of clump together, go into the liquid phase. If you continue to remove energy from that process, they no longer have enough energy to pass each other and stay in the liquid phase. They're now going to lock themselves into the solid state at that point by releasing that energy. So in chemistry, a lot of times when we have any type of process where energy is released, that is what is referred to as being exothermic. So definitely a lot of what we talk about, and we'll hit some of these topics again, obviously, in some later chapters along the way. We also look at sort of the energy component of a lot of what we do here in chemistry, and that's a really important understanding of what is happening. So again, just that idea of energy or heat flowing from hot to cold, that is really why when you put liquid water in the freezer, it becomes ice. Because when you put your liquid water in the freezer, your liquid water now is a hotter temperature, right, than the freezer temperature. That means all the heat from your hotter water, even though it's not super hot, is going to actually leave the water and go to the freezer. And that is why those guys will then lose energy. And now you will have ice cubes at that point when you put it into the freezer. Any questions on any of that there? All right, that's toothpaste. Good talk. No. I think we'll skip some of these slides, like I said before. Obviously, if we skip it, you don't have to worry too much about it. Let's talk a little bit about the scientific method here in chapter 1. And the scientific method is a really important idea of, sort of how science works. And really the scientific method usually starts with an observation. And usually you might observe something happening and go, that seems pretty interesting. Maybe I want to figure out maybe why that is happening. Or maybe you work for somebody and go, hey, I just observed this happening. And they go, that's quite interesting. Why don't you go do some work and figure out why that happened? So usually what happens after we make sort of an observation, we oftentimes want to make a hypothesis. And a hypothesis is, or a good hypothesis, is really something that can be tested, some type of understanding or idea of, I think this is happening because of these reasons. And it's actually something that you could test. You could do some type of experiment to do it. And that usually leads to, like I said, some type of experiment that is going to be done. And a lot of times this can turn into a little bit of a cycle, if you will. You do some experimentations that oftentimes will lead to maybe some more observations, some things that maybe you didn't see beginning. So maybe you need to revisit your hypothesis or come up with another hypothesis that leads to more experimentations, more observations, and so forth. So this is really sort of the scientific method, this sort of pathway of observations, hypotheses, experimentation. The goal here when you do this is hopefully at some point you could usually lead to really one of two things sort of happening. Ideally, at the end of this method, we want to maybe end up with maybe something that's referred to as a theory, or maybe something that is referred to as a law. And there is a difference between a theory and a law. and we'll talk about it here in just a second. But essentially, a theory is a understanding of what is happening, and it may be found to be not correct in all aspects of it. So it's sort of an explanation where it's not really set in stone. It can be maybe revisited along the way. Other experiments may show that maybe it's incorrect. Other experiments may show, for example, that part of it's correct and other parts are not correct. So for example, something like Dalton's law of atomic theory, I'm sorry, not law, but Dalton's atomic theory. Dalton's atomic theory is a theory that it has a lot of points to it. There's 4 different sort of main parts to it. And there are a couple parts to it that was found through later experimentation that is not really correct. Things like atoms of the same element always look the same and are identical, and that's not correct because later on people discovered isotopes, which are the same element and have different masses. So a theory is something that may not be correct in all aspects, can be revisited. Some parts of it may be correct and some parts may be incorrect. The Bohr theory of the hydrogen atom works perfectly well for hydrogen, which has 1 electron, but kind of falls apart once you get to anything with more than 1 electron. So it works really nicely to explain sort of what's happening, say, with hydrogen. But as you try to apply it to, everybody else here on the periodic table, it doesn't work very well for it. So a theory is just that. It is something that, again, does sort of explain what's happening, but it's not really set in stone in terms of it will always happen this way. It's like there's no deviation for a theory. It always is going to happen this way. And that's not really what a theory is. What that is, where we have something that no matter what the situation is, it will always happen the same way. That's actually our law. So something that's a law is something that will always happen the same way, really no matter the situation. So we have things like the law of conservation of mass, which means in a chemical reaction, we don't create nor destroy any elements. And we have sort of a conservation of elements. So for example, if we start with 6 carbons on the reactant side or the starting side of a reaction, we will end with 6 carbons on the product side or the finishing of that reaction. Those carbons may be in some different compounds and molecules on the other side, but we will start with 6 carbons, for example, end with 6 carbons. And because carbon is about 12 grams per mole, we'll have, 12 times 6 carbons on the starting side, and we'll have the same 12 times 6 of carbons in terms of the mass on the product side. Although they're in different compounds and stuff like that, we have that conservation of mass. We also have like a law of conservation of energy, for example. So we never create nor destroy energy along the way, but energy can be transformed from one place to the next. And we think about energy this way as well. We think about it as a perfect sort of transfer of energy from one place to the next. So if you're familiar with potential energy, for example, the classic example is the big giant boulder on top of a hill that's about ready to fall over. When that boulder falls over, it transfers its energy from potential energy, which is the energy of its position, to kinetic energy, which is the energy of motion. And as it continues downward, hopefully not crushing somebody underneath it, but when it hits the ground, for example, we'll move somebody out of the way. So the guy got out of the way, but it hits the ground, it's going to then transfer all that energy to the ground, right? The ground's going to basically pick up all that energy. And, so we don't really lose energy along the way. There's always this idea that if somebody loses a certain amount of energy, somebody else will gain the same amount of energy. And that's the law of conservation of energy. A simpler example as well is what we just talked about with the ice cube. When we put that water into the freezer, for example, that water will lose a certain amount of energy to the freezer, and the water loses, say, 5 joules of energy. The freezer picks up 5 joules of energy. So there's always that sort of transition. If you ever had a match or something like that, and you put your hand over it, don't do that because you'll burn yourself. But if you put it near something like fire, right, you can feel heat, right? And that fire is losing energy. Your hand is gaining energy, right? If you ever had one of those hand warmers or hand cooler type things where you crack it and it does like a reaction. Same thing's happening, right? If you're holding on to something like that, a hand warmer, and you crack that, that reaction is exothermic, which means it's giving off energy and your hand is picking up the energy, which is why it feels warm. And vice versa, if you wanted something to cool you down, you can do the same type of thing. And if you're holding on to it and your hand starts to feel cold, that is because that reaction is taking all the energy from your hand, right? And picking it up, and your hand starts to feel cold because of it. So there's this transfer of energy that happens, and there is this kind of perfect transfer of energy and these laws. So a law, as I mentioned, is really something that no matter what the situation should always occur the same way. A theory, again, is I don't want to say sort of a tentative explanation, but it is an explanation of what's happening, and it is something that you maybe can review or sort of look at again. All right, so like I said, we're gonna kind of skip around a little bit here in this first chapter and just hit some of the highlights. The other part of this chapter, in addition to some of that stuff, there is some math skills. So as I mentioned before, this class, the first 9 or 10 chapters is sort of math related. So you do need to know how to do some math. It will require you to rearrange formulas. Also think about identifying numbers. So for example, here, this number here, right, the 2 is the thousandths place, the 5 is the hundredths place, the 1 is the tenths place, and the 8 is the ones place. Here we have the ones place with the 6, the tenths, which is the 4, the hundredths and thousandths place, which is our decimals there. So again, you want to make sure that you understand, we're talking about the hundredth place, the tenth place, the thousandths place. All right. So here we'll look at some of these. Here, the tenths place is our 1. Our 5 there is the ones place. Tenths place is our 2, and our 4 there is our hundredth place. All right. Now, when we have positive numbers and negative numbers, it is important to write those if those are sort of what you get for your answers. So if you do get something that's a negative number and it's supposed to be negative, you should write it. And if it's a positive number, you should also make sure you write it. Speaking of which, on your calculator, there is also a button that does that for you. And that is the negative button, I call it. And on most people's calculators, they look like one of these 2 buttons. That is really what you should use if you need to put a number into your calculator that is negative. You should not use the subtract button, or you probably will get an error. So you want to make sure you use one of these buttons when you do that. If we add a positive and negative number together, that is essentially subtracting, right? The negative number from the positive number when we do that. So here, if we multiply 2 positive numbers, we do end up with a positive number. If we multiply 2 negative numbers, right, we end up with also a positive number as well. We multiply a positive and a negative number together, we do get a negative number in both of these cases. Also, if we do some division, 2 positive numbers will give us a positive number. And if we divide 2 negative numbers, that also will again give us a positive number when we divide those guys. And same thing here, if we have 1 negative number and we divide, we will end up with a negative number when it's all said and done. And obviously our adding will give us a positive number. Typically speaking, when we do write answers, we don't need to write the positive with the answer. If there's nothing there, it's assumed to be positive. But obviously, if you are ending up with a negative number, once again, you do need to write the negative there on there. Like here, we would want to write the negative. Adding 2 negative numbers is basically just like adding, and add the negative to the end. And adding a positive to a negative number, again, these 2 guys together basically turns that into a minus, right? And that's basically 12 minus 15 gets you to -3 when you do that. All right, so here's just some more examples. So we're kind of skip around. Let's talk about your calculator. And again, here's a picture of one and some of the important buttons on your calculator. As I might have mentioned earlier, that's where I think a lot of people run into some issues, is really how to punch these things into your calculator. So again, you want to make sure that you have your calculator with you and that you know how to properly use it. That's the negative button once again. And again, the other version on a lot of calculators of the negative button will look something like this. This is obviously your multiplication button, division, adding, subtracting, equals button. And I would say that when you put things into your calculator, I would highly recommend not to do too much at once. And sometimes that is where a lot of people run into error, is they try to put like everything in at once in the calculation. Sometimes it's better to use this important button right here, which is the equals button, several times throughout your calculation when you're punching it in. Rather than if you have a calculation, for example, like you were going to take, 42 times 125 times 1.320 and divide it by 36 and 42 and 122. Sometimes people want to put all that into their calculator all at once, and that's a really bad idea. So if you had something like this, my recommendation would be you could take as many numbers as you want, for example, up there on top, and multiply them all together. But you should find that magical equal sign at the end and hit the equals button. And then basically all those numbers on the bottom are going to be divided, right? So what people often do at this time is hit the divide button and then hit 36 times 42 times 122 and get the wrong answer. So what you should do is hit the divide button, 36, hit equals. Then hit the divide button again, 42, hit equals. Then hit the divide button one more time and go 122 and hit equals. And if you divide each of these things individually by the numbers on the bottom and hit equals after every time, you will end up probably with the right answer and not go wrong. And that again is, if you do not punch these things in correctly with like parentheses correctly, your calculator will do the wrong math for you. So sometimes it's not great to try to put everything in at once. And it's just better to kind of do it piecework, if you will. And that way, at least you'll get the right answer. Any questions on that there? Yeah. So there are a couple of ways you obviously could do it. You could multiply everything on top, get a number, and multiply everything on the bottom, get a number, and then divide the two. I will find that sometimes people will do okay on that, but sometimes people will still do that wrong as well. So sometimes it's best just the way you have it written, the sort of setup is to actually punch it in exactly sort of the way it's written. And usually if you have some numbers up on top, you could do as many as you want. The important part is just make sure you hit equals at the end of the top and then come back and individually divide it. But you absolutely could multiply both of those things separately and get two numbers and then divide it. And if you do it correctly, you should get the right answer. My experience is a lot of times people will flip numbers around and not have the right number on top and the wrong number on the bottom, and sort of make errors that way. Other questions? All right. Well, I think that's good.